Hello, everybody. This is some work I did with François Khourbiga, who is over there, resting after his talk about sound bagability. We both work at DGA, which is the French Department of Defense Procurement Agency, and we'll talk about return-oriented programming. So for those who need a refresher, this is not like we used to do 20 years ago, when France was the champion of the world champion in soccer. So 20 years ago, when you found a stack buffer overflow, you will overwrite the return address, directly write your shellcode, and jump to your shellcode, and everything works fine. So this is not possible anymore, thanks to a lot of mitigation techniques like data execution prevention, writes or executes that prevent the execution of writable pages, and in particular the stack. So instead, we can use code reuse attacks, and return-oriented programming is one such attack. It works by you first identify some snippets of code that are called gadgets that are inside the existing code, and you write in the stack the address, you override the return address with the address of the first gadget. And then when you hit the red of this gadget, you pop the second address and you go to the next gadget, which here end with a jump. So at first, return-oriented programming was focusing on snippets of codes ending with a red. Then it was extended to jump-oriented programming, and basically now we can say that it's any snippets of codes that end with an indirection. So why are we doing that? So on top of malware analysis, we are also doing security audits of software. And if we can't bypass such mitigation, our client will think that data execution prevention is enough, and he will not invest in more modern exploitation mitigation techniques. So we need to convince our clients that this isn't important to implement things like sandboxing, control flow integrity, and things like that. I'm afraid to talk about ASLR as a modern exploitation technique, but apparently it still is, since I don't know if you're aware that the Steam client got it for the first time last year, and 7-zip implemented it this year. So, okay, so get to it. So this is rarely enough, but it's better than just using dep or just not using anything. So when you want to build a ROP chain, the difficulty is to find the snippets of code, and it's not really to find the snippet of code, but to find an ordering of snippets of code that will have the effect that you desire. So this is called a ROP chain, chaining these gadgets. So there are many, many tools that can help you do that. There are two main approaches. Some tools use a syntactic approach, others a symbolic approach. So the syntactic tool, they list all the gadgets, starting from the indirection, going up a few instructions. They're very fast, but then you just have a list of snippets of codes. And if you want to look for specific gadgets, you will have to just do regular expressions on this list of gadgets. So one such tool is RP++. On the other hand, the symbolic tools, for each snippet of code, for each gadget, they compute a symbolic relation between the states after and before the execution of the gadget. This is very costly, but you can do expressive and accurate filtering. You can ask, for example, give me all the gadgets such that in the end, RCX is equal to RAX plus RBX minus 4. And one such tool is Ungrop. And all these tools, some of them actually are extended with template-based semi-automatic chaining. And when it works, it's great. But when it doesn't, you just have to grep and try to find something interesting. So what we are proposing is an intermediate approach. We will compute some semantic information, but not a symbolic one. We're just computing the dependencies between the variable in the end and the variable at the beginning of the execution of the gadget. This is a trade-off between the symbolic and syntactic approaches. This is faster than symbolic approaches and more expressive than the syntactic ones. So first, a small demo. So let's, in our case, the analyst controls a buffer pointed by RSP plus 8, which is the cell just below the top of the stack. He controls the targets of the next jump so that he can start his wrap chain, and he's looking for a stack pivot. He wants to write in the stack pointer the value that he has put in RSP plus 8. So let's try first with RP++. So the file we are looking for a gadget in is RP++ himself. We are looking for a gadget of size 5 instruction plus the return. And we'll try to see if we're lucky and is there any gadget that does exactly the instructions we're interested in. So there's none. So now can we at least write in the stack pointer? Okay, so there are a lot of gadgets that allows us to write directly with a move. So if it didn't work, we would have to try another instruction like load effective address or things like that. There are some that are very nice, like, okay, if this disappears below the move RSP RCX red, we have move RSP RBX blah 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 red, move RSP R8. So we have a lot of gadgets that are great for stack pivot, but we didn't find our gadget yet. So now we'll try to look for gadgets that read from the cell we control, RSP plus 8, and write it in a register. So there are a lot of them, and so this is great. Again, we have here our move RBX RSP plus 0x8. Unfortunately, the gadget ends with a red, and we haven't done our pivot yet, so we can't chain this gadget with the move RBX, RSP RBX that we found before. So there are a lot of gadgets here that we can't use. So let's just get rid of all the gadgets that end with a red, and look for, again, gadgets that don't end with a red, but write in a register from RSP plus 0x8. So there are quite a few of them. But again, this one ends with a call keyword RAX, but we don't control RAX. It comes from RDX, and we don't control RDX. So we have to continue grabbing into our file of gadgets, and this can be cumbersome. So now let's try ongrop, which is a symbolic tool. So it's complaining a little bit. And then, okay, something very interesting is that ongrop is saying that our binary is too big. So it's something like between 1 and 2 megabytes. So this is too big for ongrop. So it's enabling fast mode. So why not always using fast mode? It's just because basically what fast mode does is not analyzing all gadgets. So it just decides that some are too complicated, so it just drums them. And now we have to wait. Okay, maybe I can suggest that we all go grab lunch. We come back, and then it be done maybe. No, I'm just kidding, this is a video, so we'll just skip to the end. Okay, almost done. So now I will just print, ongrop, I'm poking fun at ongrop, but I think it's a great project when it works. So we can look at all the stack pivots in one gadget that it found. I put a slip here so that it doesn't go too fast. And so it found some. And if you can read fast, maybe you will be surprised that it didn't found the move RCX or the move RSP RCX red. So this is surprising. And ongrop allows you to do automatic chaining, and also you can set a register to a given value. But if you try it with RSP, it doesn't work because it only works with general registers. And so you can choose ungrop in this setting. And again, I poked fun at ungrop, but I will have to skip to the end too with my proof of concept. So by the way, so this is like 8 minutes. So if we deactivated fast mode, ungrop would have run for like 45, 50 minutes. So now we'll print all the registers from which I can influence RSP. So there are quite a few. We have our RCX here, and a few other like pseudo registers on the stack. And now an ugly script where we will just loop over all these registers that can write directly to RSP, and we'll start from stack top +1, which is the cell we control, and loop over all the gadgets, find the ones that have an influence from our register to this temporal register, and such that we can chain to the next gadget. And then we will do the same for our second gadget, and it will suggest a few chain in 2 gadgets that does a stack FIVO. So the first one is not that great if you really look at it, and the second one is much better, and then there are a few others eventually. Okay, let's look more details to the one T-Brop outputted. So this is this chain of gadgets. So we have our move RCX keyword pointer RSP +8, and then move RSP RCX, right? And the interesting thing is that the tool outputted this gadget because it also detected that we control the instruction pointer at the end of this execution, because array X is written from RCX, and RCX is a function of RSP +8. So grabbing our way into finding these 2 gadgets is possible, but here we just have to wait for a few minutes. It suggests like a dozen of chains, and there was one that was interesting in it. So we're not saying that the tool is solving every problem, but when other tools fails, it can do an interesting suggestion, this tool and this approach. So as I said before, it's a trade-off between the symbolic and syntactic approaches, and it's taint-based. So it means that, for example, if we consider this 4 instruction, the exchange the taint between RX and RBX. The XOR will remove the taint from RCX. The add RCX RX will propagate the taint from RX to RX on RCX. So this taint propagation can be represented by this array, which can be written in the following way. If you consider the first line, it means that RAX at the output of the gadget is a function of RBX in the input of the gadget. Second line, RBX is a function of RAX, and RCX is a function of RBX. And this array can be represented as a matrix. So I just exchange the arrays, replace it with the arrays with 1, and the dot with zeros. The zeros are grayed out because those matrices are very sparse. We don't need to represent them explicitly. And what's interesting about this representation is that we can do computation. And this matrix can be computed by taking the product of the matrices of each instruction. And more importantly is that, as I said, gadget is a snippet of code that terminate by an indirection. So here on the screen, we can see 4 gadgets, the ones that just contains the jump, the one that contains these 2 expressions, the one that contains 3, and the 4. And actually, if you want to compute as dependency matrix of the full gadget once you have computed a partial one, you just have to multiply if you want to extend your gadget by one instruction, you have to do a product with one matrix. So you can do all the computation very efficiently and reuse the work you did for other gadgets. But these array and matrices are also equivalent to graphs. So we can represent the taint propagation with this simple graph. RX goes to RBX, and RBX goes to RX and RCX. And what's nice about this representation is that they can do gadget superposition. So let's consider these two gadgets. On the left, we have a gadget with its graph. On the left, another gadget that does a push pop, which gives us a dependency between RBX and RDX. And if I overlay the graph of the two gadgets, I get this graph. And the interesting thing is that then I can see that there's a path from RAX to RCX that goes through a full arrow, so which means a gadget on the left, then a dotted arrow, gadget on the right, and a full arrow gadget on the left. So even though none of the gadgets allows you to influence RCX from RAX, by combining those first left, right, left, you can have a chain that gives an influence from RAX to RCX. And computing this graph is very easily, because if you take the matrix representation, it's just the sum of the two matrices. So here we are using Boolean matrices, so the sum is really just the disjunction component-wise of the two matrices. So if we combine superposition and chaining, we can also do interesting stuff. So as I said, the sum of the matrices of two gadgets is the effect of applying one or the other. If I take the sum of all the matrices of all my gadgets, I capture the effect of applying any one gadget. If I add to this matrix the identity matrix, which basically is the matrix of a NOP gadget or no gadget at all, I get a matrix that can represent the effect of applying 0 or 1 gadget. If I take the square as a matrix of applying 0, 1, or 2 gadgets, and if I continue squaring each time, it will saturate in a few steps, and then I get a dependency matrix that encompasses the effect of any chain of any length of gadget in my set G. And if the dependency I'm interested in is not in this matrix, it's useless to even try to do a chain because it's not possible. So it means that I will have, instead of trying to do a chain, extend my set of gadgets by trying to find bigger gadgets. Conversely, if I find the dependency I'm interested in, it doesn't mean that a chain exists for several reasons. First, because we are doing some over approximations, and second, because we are not considering here the chain condition. The chain condition is basically the condition that tells you that you can chain your gadget with something else. If you consider this one, and if you're just using a syntactic approach, you may think that this gadget terminating with a red will take, you may think that you need to control the stack in order to use this gadget. And actually, this is the hypothesis we did when I showed you the demo with grep, with RP++. I got rid of all the gadgets ending with a red because I didn't want those. And actually, some are interesting because this one, its condition is that you need to control RAX to be able to chain this gadget with something else. And you can see it because you write RAX in RSP plus 0x50, and then you add 0x48, you pop, and thus on the red, on the top of the stack, you have the value of RAX and not a value that was on the stack before. So if all you control is RAX, you can use this gadget. And you can detect these kind of things. You don't need symbolic approach. You can just do it with our dependency approach. So I didn't say how we handle memory and stack yet. We have two approaches, a correct one, which doesn't have any false negative. We use just one pseudo register, which we called mem for memory. And basically it means that any read on memory depends on every write that are above. So this allows us to have no false negative. And we capture all aliases and more. And there's another approach which is more useful, which has much less false positive but some false negative. We use two pseudo registers for memory, mem write and mem read, which are used in the following way. Any read operation on memory create a dependency coming from mem read, and any write in the memory create a dependency to the pseudo register mem write. We also have a pseudo stack and one pseudo register for each cell of this pseudo stack. This is what allowed us to detect that we are writing in the stack and that the rate is actually popping regex. But we can only do it for a finite number of cells and a pretty small one, like 50 cells we used. So we have two accumulators on top of the stack and below the stack. And we also, I didn't talk about, introduce another pseudo register that we call deref to track dereferencement. So here we can also say that RSP was dereferenced during this gadget. So as an example, if I have a push arrayx followed by pop RBX, and this array representation, this is read in the following way. RBX comes from the top of the stack, and the top of the stack comes from arrayx after the push arrayx. And similarly, the top of the stack after the pop comes from the value that was just below the top, and this value comes from the top of the stack. So we did a proof of concept implementation of our approach in Python 3 using capstone, CP, numpy, and lief just to extract the text section of binaries. CP and numpy were used for Boolean matrices, actually sparse Boolean matrices manipulation. And we used capstone for disassembly, and also the next branch of capstone allows you to get all the registers that were read or written by an instruction. And that allows us to since we are pretty lazy, to just have the semantic of every instruction, because we just said that every register that is written depends on every register that were read by the instruction. So we just had to add a semantic for instruction manipulating the stack pointer, like pop, push, call, write, leave, enter, extra, and add sub RSP with something small value. And here are the results. So the first two columns are R++ and WAP gadget. Those are a syntactic tool. The last two are ungrop and nwrap. So for ungrop, we deactivated the fast mode because we thought it wasn't fair. And ungrop also is multi-threaded, so it was taking advantage of this. And our proof of concept is just in between. So I'd say that this really is a trade-off between the two. Yes, I'm done. So as a conclusion, our contribution is a new approach for gadget filtering, which presents a symbolic syntactic trade-off. We use dependency matrices and chain condition. We can do cool stuff with gadget superposition, and there's a throwaway script on GitHub. And the perspective are to investigate the link between shortcut fast and semi-automatic chaining. This is not entirely new, but we are applying these shortcut fast algorithms to something much bigger than usual. and the interaction with symbolic approaches that could filter out the suggestion done by the tool, but on a much smaller set of gadgets. And actually, that would be nice to transform our ugly proof of concept into a real tool. Thank you for your attention. If you have any question.